So welcome to the first section of Chapter 7 on atomic theory. Gotta be honest here, a lot of this stuff is probably stuff that you aren't going to use in your everyday life, but what's coming in the next chapter, which is probably the most important section of chemistry in your junior science year, really is based an awful lot on some of the research that these dudes did a long time ago, and I am a believer in the theory that you probably should know where you've come from in order to get to some new destination. So you don't head out in some wild direction without kind of knowing a little bit of the background. So the atomic theory probably starts with a Greek dude by the name of Democritus, but in your textbook, section 7.1, which you should read, by the way, you're going to find that there's an emphasis on just the contributions of 4 characters. One of them is Dalton, and the other one is Thomson, Mr. Rutherford, and then Niels Bohr. Each of these came up with theories that were developed or based on the previous guy's research or discoveries. Each of them, in order to remember their model of the atomic theory, it's probably a good idea to know the nickname that they're remembered for. So in the case of John Dalton, you want to think of his model as the billiard ball model. And you've all seen billiard balls. There you go. We'll get into the details as to what goes in these lovely little boxes, the differences from previous theory, similarities to previous theory. You should have that, of course, as a handout. This is an assignment for 7.1. So, yeah. So, J.J. Thomson, this fine-looking gentleman, was the next scientist who took the research of Dalton and came up with a model which is called the raisin bun or the plum pudding model. Right now those little raisin buns look really good to me. Then there was another discovery, and the discovery was by Rutherford, who did some really cool experiments, which you, by the way, should watch at least one of the little videos online that show this experiment. Make sure you understand what the results of that experiment were and why it led him to come up with this planetary model. If you don't, do make sure you ask me and we'll talk about it, right? So the planetary model looks like a planet to me. The final model that you will worry about, and of course you should realize in this modern age that we've moved beyond even Bohr's model, but for our purposes we're going to stop with Niels Bohr. Bohr came up with a model called the solar system model, with electrons orbiting a nucleus, the nucleus containing the proton, and then these negatively charged electrons at more or less fixed levels outside that nucleus. So before we get to filling in this lovely little table, you should probably get a little review on the background here. So we're moving right along. Basically, we're going to give Democritus, back in 500 BC, credit for coming up with this term atomos, simplest or the smallest part of an element. And diagrammatically, you might look at an element as made up of these particles, where all the particles are the same. Every element is composed of only one type of atom. Carbon is made up of carbon atoms, chlorine is made up of chlorine atoms, and iron would be made up of iron atoms. Duh. An atom's atomic structure. Here's where it's important. Why are we doing this? I mean, who cares about the structure of an atom? In all of the chemistry you look at, chemical reactions, it's actually this atomic structure which determines both the physical, what it looks like, what it feels like, what temperature it melts at, all that kind of thing, and its chemical properties. What does it react with, and what does it give in those reactions? That's what chemistry is all about. So some elements have similar atomic structures, and thus they have, Lovely word. They have similar chemical properties. You've already met the periodic table. So what that periodic table does is organize matter, the elements, based on similarities in their chemical properties. And those similar properties are again a result of similar structures. So when you look at a periodic table, you should be able to name 3 pairs of elements that you would predict to have similar atomic structures. And then you should be able to describe the similarity in each case. Maybe at this point you probably wouldn't feel too comfortable with this similarity idea, but I would take a periodic table, and what I would do, I would essentially look at things like, okay, these are the halogens down here, this family. By the way, there are 18 groups. You go across vertically from 1 to 18. Group 18 are called the noble gases. They all have 8 electrons in their outer shell. They are full, they're happy, they're content, they don't want electrons. On the other hand, way back here on the left-hand side, you would say these guys are actually very eager to get rid of 1 electron. And we'll get into, of course, more detail as to what happens here. But if you look at these ion charges, 1 plus, 1 plus, 1 plus, that tells you something. That tells you that all of these elements in this family, the alkali metals, have a tendency to give up 1 electron. Electrons are negative, so if you give up something that's negative, guess what? You become more positive, so they are 1 plus. But that previous question, look for a pair of elements that have similar properties. I would pick any 2 elements in any family, right? So over here in group 17 are the halogens. If you take fluorine and chlorine, both of them have 7 electrons in their outer shells. They both have a tendency to want to grab 1 more electron to make it 8, just like the noble gases to their right, neon and argon. On the other hand, just to the left of them, oxygen and sulfur, notice that they gain 2 electrons and become -2 ions. And I know right now this concept of ions is beyond where we're supposed to be at this point, but it does kind of help to look at the properties. At a simpler level, basically you could look at any one of these families. Group 2 are the alkaline earth metals. All of these elements have very similar properties and they will react in a similar way. So that's really what we're after at this point. We will get into more of the details of these ions and losing electrons and gaining electrons later when we look at actually forming compounds. But for now, the atomic structure very much determines chemical and physical properties. So here's the key ideas in Chapter 7. Matter is made of atoms. You knew that. The atomic theory of matter has changed with new discoveries. We have Dalton, we have Thomson, we have Rutherford, we have Bohr. There they are. That's why you have that little piece of paper in front of you, right? These elements, of course, can be classified according to their properties. We just mentioned that the structure actually determines their chemical and physical properties. So notice the key vocabulary words in this chapter. If you're not familiar with where the nucleus is and what it contains, protons and neutrons, the fact that electrons are subatomic particles, yeah, you probably should read 7.1. So each element has its own kind of atom. Atoms of different elements may combine to form compounds. The discovery of the electron led to Thomson's raisin bun model of the atom. So if I had to draw a raisin bun, this would be my raisin bun, where you have all of these electrons, raisins, dispersed randomly throughout the bun. Of course, that's not the current theory, but it was one step towards Niels Bohr's ideas. Thomson's model was then modified by Rutherford. Rutherford's discovery of something called the nucleus required a new model, one with most of the mass concentrated in a small space at the center of the atom. In other words, the discovery of the nucleus really changed things in terms of what kind of a model we're looking at. So now we have a nucleus with the protons at the center and the neutrons, which by the way have no charge. Protons have a positive charge, electrons a negative charge, but we have this very dense mass in the nucleus and orbiting, so to speak, at various levels outside that nucleus are electrons. So 7.1, let's start with Dalton's theory. This is where you should grab that sheet. We're basically looking at Dalton's differences from the previous theory, and there's not much before him. There's going to be Democritus. Dalton, of course, had this billiard ball model. The differences are that each element has its own type of atom. Democritus would have said, no, that's not true. All atoms are the same. All atoms of an element are identical. An atom is indivisible. You cannot divide it. Compounds are formed when two or more atoms are joined together. And by the way, the wonderful thing about video is that you can stop this at any point and go back. You can pause it. Unlike the classroom situation where everybody would kind of demand, slow down, speed up, etc. You now have the option of just, hey, I need to take a break here, need to go get myself a cup of tea. I'm going to come back to this later, so don't hesitate to do that. You can, be flexible. So these were the differences that Dalton had. The similarities to Democritus's idea of the atom were basically that matter is made up of atoms. That's about it. So not much to write down there. Let's move on to Thomson's raisin bun. So again, you might be asked to actually draw a model of these various theories. So you practice drawing a raisin bun sometime. Better yet, make some raisin buns and give me one, okay? So differences between Thomson and Dalton. Most of the atom is a positive mass. Now that's interesting. Negative electrons are evenly distributed throughout. And the similarities were that matter is made up of atoms. Each element has its own type of atom. All atoms of an element are identical. And finally, compounds are formed when two or more atoms are joined together. So you might want to reread that, but those are the differences and the similarities between Dalton and Thomson. Who comes after Thomson? How about Rutherford? Rutherford is the planetary model guy. So differences here. Positive protons and neutral neutrons are in the nucleus. So up until this point there's been no mention of a nucleus. Now we have a nucleus. The nucleus is a very small space in the center of the atom and makes up most of the mass. Electrons orbit around the nucleus like satellites around a planet. There they are. And elements can have several isotopes. Isotopes you really don't go into in much detail until next year, but you should be aware of the fact that when you look at a periodic table, those masses that you see for each of the elements, they're not really nice round whole numbers. They tend to be any degree of decimal points after the whole number, and that's because you have each element may have more than one isotope. It means the nucleus contains more or less neutrons. Really encourage you to, again, on the website, check out the lovely little link to a reading or two on isotopes. Rutherford's theory was based on evidence. He didn't just make this up. Two very famous experiments. Same experiment, two videos that show it. Video 1 and video 2. I am not going to go to it here because it's available to you on the website, but if you actually go to this PowerPoint, these links are active and you can go to it that way as well. So finally, the similarities. Matter is made of atoms. Each element has its own type of atom. By the way, if you want to just go ditto for these similarities, you'll notice they're pretty much the same as the ones before. Compounds are formed when two or more atoms are joined together. That brings us to the last chapter, so to speak, of 7.1. This would be Niels Bohr solar system model. Can you draw a solar system? And excuse me, but I don't want to stop recording because you know what? It just takes too much time to get going again. So this is what a solar system model would look like. You should be able to draw a nucleus, realizing that there are protons in there and neutrons. And then the electrons are going to be distributed around the nucleus, 2 electrons in the inner shell, and then up to a maximum of 8 in each subsequent shell that we add. And the number of rings, so to speak. We'll get into how you know how many are there. But differences. Electrons orbit the nucleus in specific, allowed orbits or shells. When we say specific, we may be talking about probability here and clouds that you may find them in. But as you can see from the model, it does suggest that at any particular time, electrons can be found at certain energy levels. So electrons absorb or emit energy to move between shells. So in this chapter, you will actually do flame tests and note various colors that are emitted by certain elements, and those elements have these unique colors when they are flamed because they're giving up electrons, or the electrons are moving from one shell to the next. So you should make sure you are comfortable with the idea that the order of number of electrons in these shells is always 2 in the first, always 8 in the second, and 8 in the third. And again, you don't have to worry about going beyond 20 elements in this course. It does get a little more complicated later. Bohr's solar system model, similarities. If I'm not mistaken, these are exactly what you already have. Boom. So, just a matter of you filling out that lovely little sheet, and probably more important would be you now going to the website and looking at the little animation on Rutherford's experiment and checking out the link or two on isotopes. We are going to focus for the rest of our course in chemistry on a model very similar to Bohr's. So you'll get used to actually drawing these lovely little models before we get out of this chapter. So thank you for coming.